One of the outstanding features of engineering technology in modern times has been the progress made in the field of hydraulics. From the hydraulic press of 180 years ago to the straddle carrier in the modern container terminal, ingenious ways of harnessing the simple principles of this branch of physics have been discovered. A touch of a hand on a lever, the subsequent movement of fluid, and a 40-ton container may be lifted with ease and put down in another place. Only the hydraulic method of power transfer can handle such huge loads with such fine control. The transmission of hydraulic power is divided into two parts, hydrokinetic and hydrostatic. Hydrokinetic systems depend on the use of the hydraulic fluid as a vehicle of kinetic energy. The velocity of the moving fluid provides the power. Hydrostatic systems are those in which the primary function of the hydraulic fluid is transmission of force and power by pressure. This film is concerned with hydrostatics. Probably the most familiar example of hydrostatic power transfer is in the hydraulic braking system. At its most sophisticated in the disc brakes of racing cars. And at its most powerful in the servo-assisted hydraulic systems of modern commercial vehicles. To understand how hydrostatic systems work, we must examine the properties and behavior of liquids. Liquids are free to flow. Unconfined, their flow is controlled by the force of gravity and the nature of the surface with which they are in contact. This is because the molecules which make up a liquid form a compact but highly mobile mass. The rate of flow of a liquid depends upon its viscosity. Water has a low viscosity and flows freely. Oil, which is used in most hydraulic systems, has a higher viscosity and flows less freely. In this apparatus, the pressure on the water inside a glass bottle is increased by the movement of a small piston. The compact molecular structure of liquids makes them virtually incompressible, an important factor in hydrostatic systems. And because of this, the increases in pressure are transmitted directly to the bottle. This container has necks of equal area, and the downward pressure on one of the pistons is clearly transmitted to the other. Pressure exerted upon a confined liquid is transmitted undiminished in all directions and acts with equal force on equal area. This is Pascal's law of hydrostatics. The principle applies however far apart the two pistons are, or whatever shape the vessel connecting them. If we modify the apparatus and increase the area of one of the pistons, the volume of liquid displaced by the downward movement of the smaller piston remains the same. But because of the increased area of the larger piston, the upward movement is proportionately less. And the force transmitted from the small piston is magnified at the larger piston because of the increase in area. So that if a load is added to the large piston, it can be raised by a proportionally smaller load. It is this application of Pascal's law that forms the basis of all hydrostatic machinery, large or small. To make practical use of this apparatus, specific mechanical adjustments have to be made. The fluid which is displaced to move the larger piston must be retained. And to do this, a non-return valve is introduced between the two cylinders. Because displaced fluid is retained by the non-return valve, no further fluid is available for work in the smaller cylinder. This is overcome by the introduction of a reservoir and supply valve. We now have a system capable of raising a load, but to lower it again, we have to transport the fluid which is built up in the large cylinder back to the reservoir. This is a simple hydrostatic device for the raising and lowering of a load by hand, as for example in the hydraulic jack. The vehicle is raised short distances at a time by large movements of the jack lever. The lever is connected to a small piston which pumps oil from the reservoir through the non-return valve. Each forward stroke of the piston injects a small volume of oil through the valve to the ram of the jack. Successive pumps on the piston extend the ram and raise the jack. The oil release valve allows the jack to be returned to its starting position, ready for further use. But this and others like it are simple applications and limited to the power of manual operation. This limitation is overcome by the introduction of an alternative source of power, the pump. The car lift operates in this way. This one can lift 2 tons. The pillars contain the rams, and the electric pump provides the pressure. So far, we have seen simple lifting and force magnifying applications of the hydrostatic principle. Sophisticated applications require a system that controls the movements of the piston in both directions, which means that hydraulic fluid is introduced to both sides of the piston. To allow the pump to be used for both control directions of the piston, additional pipes and a control valve are required. The control valve allows the pressure provided by the pump to be directed to either side of the piston, depending on which direction the work is required, and enables the fluid from the exhaust side of the cylinder to return to the reservoir. The immense controlled pressures on the jaws of this crusher that reduce motor cars to compact packages for dispatch to the furnaces could not be achieved in a unit of this size without the application of the hydrostatic principle. This hydraulic extrusion press transforms a billet of aluminium into angled sections for window frames. The ram exerts a pressure of 1,600 tons on the billet, forcing it through a die, which is a cross-section of the shape to be produced. This reversing hot rolling mill is one of the largest of its kind in the world. Hydraulic rams provide the huge forces necessary to reduce the thickness of this 5-ton aluminium ingot by up to 70 millimeters every time it passes under the rollers. In this automatic drilling and shaping machine, the path of the milling tool is programmed on a computer. Hydraulic power controls every movement of the tool, and provides the force necessary to remove up to 300 cubic centimeters of metal a minute. Much of the machinery of ships at sea is hydraulically operated. The rams of the stabilizers work by hydrostatic power and reduce the roll of the ship in heavy seas. Modern earth-moving machinery would not be possible without the power and precision of hydrostatic rams. In aeroplanes, hydrostatic power is used to operate the controls. The pilot provides the initial power by movements of the control column and foot pedals, and these are transmitted to the control surfaces of the aeroplane. The engines drive the hydraulic pump, which supplies the power necessary to operate the flaps. After takeoff, hydraulic rams retract the undercarriage. Small movements have a large effect when the plane is in flight, and the hydraulic systems ensure that these can be carried out with great precision. Hydraulics have fulfilled the need for a compact source of accurately controlled power by applications of the principle that Pascal formulated in 1647, that pressure exerted upon a confined liquid is transmitted undiminished in all directions and acts with equal force on equal area.